Hello, this is a pre-recording of Chapter 20, Activity 1. We're going to start out with doing some nomenclature of aldehydes and ketones. And there's some instructions here. It says, make sure to remember that when you have both an aldehyde and a ketone, the aldehyde gets priority as the parent, and ketones are named as an oxo substituent. Both aldehydes and ketones have a higher priority than an alcohol. So alcohols would get named as a substituent and be called a hydroxy group. And alcohols, of course, have a higher priority than a alkane or alkyne. And no priority would be alkyl groups and halogen substituents. So in this case, we just have a ketone. So we're going to name it with the ending ONE. And if it was a alkane, it would be cyclohexane. So it becomes, drop the E, add the ONE, cyclohexanone. Because we're naming it as a ketone, we don't need a 1 by definition. There's only one carbonyl, and it's at carbon number 1. Okay, we have another cyclic ketone. In this case now, we have some methyl substituents. When we're naming it as a ketone, and the priority or the numbering starts at the carbonyl carbon. 1, 2, 3, 4. We have 2, 4, dimethyl, cyclopentanone. Don't forget the cyclo is important as part of the parent name. All right, moving on. In this case, now we have an aldehyde. We have to start at the carbonyl carbon. Aldehydes are always at the end of a chain, right? So they're by definition always at carbon number 1 when you're naming it as an aldehyde. We actually don't need to include that number. Then we would, from here, it looks like a longer path to go this way. However, if we go this way, we'll have more substituents. We want to include that alcohol. Okay. So we're going to go this way. And now we have a hydroxy group and a propyl group. And H comes before P. Okay, so we'll do 3 hydroxy, 2 propyl. And now comes the parent, a 4-carbon chain. So that would be a butane. That becomes, drop the E, add the AL, so butanal. Next, we have a ketone and an alkyne. We want the lowest number possible for the carbonyl carbon. So we'll start on the right. And there are technically no substituents here. Let's get on with the parent, and the parent is going to include the triple bond. I'm going to do F3 ine, making sure to include the number and where that triple bond comes. So Hep3 ine -2O. So instead of a heptanone, it's a heptinone. You just want to make sure to include the locants for the alkyne and the carbonyl. So with the ketone, the carbonyl doesn't have to be at carbon number 1. In fact, it can't be at carbon number 1. We always include the number for the ketone, unless it's cyclic. Okay, moving on. So from here, we're going to name this as a ketone. Right, so we're going to start from the right there to get the lowest number possible for the carbonyl carbon. And in this case, we have a stereocenter. It is, so the priority groups are chlorine first, then the fluorine, and then this carbonyl group. Right? So you can kind of imagine looking down this carbon number 4 bond. Right? We to go from chlorine to fluorine to the carbonyl, it's a counterclockwise. So this is S, and now we have the 2 substituents, the fluoro and the chloro. Right? Chloro comes first alphabetically. So 3 chloro, fluoro. Now the parent, right, which is a butane, 4 carbon chain. So again, we always include the number for the carbonyl carbon for the ketone when it's acyclic. When it's cyclic, it's always at carbon number 1. You don't need to repeat it. In this case, if you're thinking about should I count this way or this way, double bonds have a higher priority than alkyl groups in this direction. So we have 2 substituents, 5, 5 dimethyl. And then now comes the parent, making sure to include the locant for the alkene. This is a cyclo. Normally, if it didn't have an alkene, it'd be a cyclopentane. Now it's a pentene, right? So cyclopent 2-ene. And you could put a -1 in there if you wanted, but it's not necessary. Okay. Over here, remember aldehydes have a higher priority than ketones. We're going to name this as an aldehyde. And the ketone is actually a substituent in this case. It's going to be an oxo group. We have 2 substituents. By the way, this might look like a chiral center, but remember it's not. And so no chirality information is needed. The 2 methyl groups are the same, so it's not a chiral center. Okay, so the substituents are a methyl at carbon number 4 and the oxo group at carbon number 2. M comes before O alphabetically. So 4 methyl, 2 oxo, and now comes the parent, which is a 5 carbon chain, so a pentanal. And again, we don't need a number because by definition, when it's acyclic, the aldehyde is always a carbon. Okay, and then over here, naming this as an aldehyde. I want to start there. We have a 5 carbon chain, 2 substituents. We have a methyl at carbon number 4 and a hydroxy at carbon number 2. So H comes first. So 2 hydroxy, 4 methyl, and then a pentanal. Whenever I see a double bond, I think to myself, is this E or Z? And if so, I would put that information here at the beginning. But because it has these 2 identical methyls, it's neither E nor Z. No. Okay, moving on to the review. Synthesis of aldehydes and ketones. So first, we're looking at ozonolysis. And if we do ozonolysis, we cleave this carbon-oxygen double bond. And because there's hydrogens here, we end up with an aldehyde. Right, so we can kind of keep it looking like it is and flip the aldehydes out. Or you can think about the fact that you know there's a 6 carbons and then there's 2 methyls. So this would be also equivalent to drawing it out in a more linear fashion. And we've got the methyl there, methylene, methyl, and the other aldehyde. You can always double check that you have the right number of carbons. Okay, so we're going to be doing again ozonolysis here. But notice how there are not any hydrogens attached to it. So we're going to get 2 ketones in this case. And because of the rotational symmetry, it's going to be the same compound. So you really only get one thing. You just get 2 moles of it for every mole of this. So the ketone would look like so we can always double check. Methyl, carbonyl, CH with 2 methyls. You get 2 of these, but I really don't see the point of running that twice. Okay, next we are doing, starting from an alkyne, we're doing hydroboration oxidation. I don't like seeing it this way. Normally people would use a bulky chlorine, like 9-BDN, when starting with an alkyne to avoid undesired side reactions. So, but anywho, what this does is anti-Markovnikov hydration, which gives you an enol, which tautomerizes to an aldehyde. So we would have cyclohexane ring, 2 carbons, right, where this carbon is going to be an aldehyde. But remember, we're not adding or deleting carbons in this reaction. Make sure however many this has should have the same. Next, we're doing the Markovnikov hydration of the alkyne. So this also gives you an enol that tautomerizes. In this case, because the OH group ends up at the more substituted carbon, you end up with a ketone. So these are both in the alkyne chapter. We need to review those. So we get the methyl ketone. And then this is an electrophilic aromatic substitution reaction, specifically a Friedel-Crafts acylation reaction. Remember, this is an orthopara director. So we can put in that acyl group in the para position. And notice how all of these reactions produced aldehydes or ketones. So just because we're finally at the aldehyde and ketone chapter doesn't mean it's the first time you've ever seen an aldehyde or ketone. These are just some of the review reactions, but don't forget you can also make aldehydes and ketones through oxidation of alcohols, which is not reviewed here. Okay. Going on to some new reactions in this chapter, we're going to start talking about forming an acetal. Okay. And you can form an acetal from an aldehyde or a ketone. And in this case, we're using a ketone. And so then there's 2 R groups here. So at this carbon, right, there's 2 R groups. But if you had used an aldehyde, for example, methyl is a hydrogen, then you would just have a hydrogen here. But the reaction would work the same way with either an aldehyde or a ketone. And this reaction uses typically some sort of alcohol and then catalytic strong acid. So just to keep things simple, we're just going to use HA for the acid and then the conjugate base of the acid. So we can either do proton transfers where we protonate something with this, or we deprotonate something with that. And it talks about drawing in lone pairs to satisfy indicated formal charges. So that's always a good idea with the mechanism to draw in all the lone pairs. And then the last thing it asks us to do is curved arrows and tell if it is a nucleophilic attack, loss of a leaving group, proton transfer, or rearrangement step. This is just bringing it back to the fact that we've seen mechanisms really primarily follow a lot of these simple steps. So recognizing which one is helpful. Okay, so when you treat a ketone or an aldehyde with a strong acid, right, whenever you treat something with a strong acid, you should expect the most likely thing that's going to happen is the strong acid will donate a proton. Okay, so we're going to show a proton. Instead of writing A, B, C, D, I like to just write. It takes a little bit more time, but better for review to actually see. Those are the arrows needed for a proton transfer. Now we have this protonated carbonyl. Now the oxygen has a full positive charge, and it is resonance stabilized, right? So the partial positive charge on the carbon as well. Really, the oxygen and the carbon share positive charge. That makes the carbonyl carbon highly electrophilic, because now it's got an even more significant partial positive charge than it did before the proton. So even a weak nucleophile can do a nucleophilic attack here when after you've protonated, because we've generated a stronger electrophile. So we can now show a nucleophilic attack. There's a problem with drawing only one arrow. Right? We cannot exceed the octet on that carbon. We need to send electrons up to the oxygen. So this is a nucleophilic attack. Right? And we can see what's happened when you look at the product. Don't forget to draw in any lone pairs as necessary. And then we see from here to here, we're just losing a proton. Immediately drawn in the base of the acid. We'll just use that to deprotonate. Another proton. Notice now that we've reached something that's named, right? We're trying to get to an acetal, and we go through what's called a hemiacetal, which basically stands for half acetal. So noticing when you have a carbon with an OR group and an OH group, that is a hemiacetal. And you should be trying to target that as a key intermediate in getting to the acetal. The hemiacetal is typically still very reactive, not super stable, so it continues reacting. The exception is if it was cyclic. We'll eventually talk about that. But the goal here is, right, and we always want to keep in mind what are we trying to do, right? Trying to get to this acetal with the two methoxy groups. And now I have one methoxy group, right, and one OH group. So this needs to go. This is going to leave, right? So I need this to be a leaving group, this OH group. If it's a leaving group, I can get rid of it. And I can replace it with a methoxy group. So the goal is to get this to be a good leaving group. Right? So what can we do? We can just protonate it. So once we protonate it, so another proton transfer. Now we have a good leaving group. Water is a good leaving group. Drawing some lone pairs. Right? And we can go ahead and have it leave. Have it leave, but in order to get this resonance contributor, I also need to generate a carbonyl there, that lone pair. That kicked out water as a leaving group, and now I have a carbonyl here. Oxygen is positively charged, so it's highly electrophilic. So another methanol nucleophilic attack, don't forget, move electrons up to oxygen. So now we're really close, right, to the final product here. We just need to leave this final and proton, the final proton transfer. It's like I've forgotten to label, so I'll go back, loss of a leaving group. Okay, this is a nucleophilic attack. And proton. If I forgot any lone pairs, I'll go ahead and add it. Okay, and now we are done. I think we did everything that the instructions asked us to do. By the way, all of these steps are reversible. Notice how he does just have a regular forward arrow, but that doesn't mean that the steps are not reversible. Right? And in acetal formation, everything is completely reversible. So, and we're going to see that later on in the next. Okay, so now is the chance for us to practice our skill. Right? We have now another case. It's a little bit, maybe a little bit more challenging because it's going to be forming a cyclic acetal, so it's different. But all of the steps that we just drew are going to happen. And notice how he says, make sure to go through the hemiacetal, en route to the acetal. So he's giving you a clue here if you need to hit intermediate. Instead of having an alcohol in solution, now we have a diol. When we have a diol, we end up with a cyclic acetal. All right, so let's start with the mechanism. Remember, when drawing a mechanism, it's important to draw in lone pairs. So we can draw in some lone pairs, and we're going to protonate. Remember, strong acid is the most likely thing that's going to occur here. That activates the carbonyl-carbon to become even more electrophilic. Formed here, proton transfer. We have the protonated carbonyl. We also have A with a lone pair, which we'll use later on. And at this point, remember in the previous example, the alcohol attacks here. So instead of the alcohol, we're just going to use the diol. Same really. We've done some lone pairs here. Do our nucleophilic attack. Make sure to think about exactly what form that nucleophilic attack. And all lone pairs and formal charges to get to the next intermediate. Okay, so now we're at this situation where we have a intermediate with a formal charge. One thing I want to point out is what we don't want to do is ever have an intermediate with two of the same formal charge. So if we look up here, one of the things we'll notice the mechanism is that we went from neutral to one formal charge, neutral, one formal charge, one formal charge. So at most, we only ever have potentially one formal charge, one positive charge. And under acidic conditions, notice how it's always a positive charge. The only type of negative charge you could have under strong acid conditions would be the conjugate base potentially to the strong acid. Right, so a very, very weak base basically is possible in acidic solution, not a strong base. Okay, so don't generate anything with a negative charge unless it's a very, very weak base. And also don't have an intermediate with more than one positive charge. So this is really things that help you remember what to do next. Kind of keep those rules in mind. Coming back over here, so you might be thinking, well, gosh, I really want to get rid of this as a leaving group. I know it's not there in the product. I use water, protonate it, make it leave. The problem with protonating it right now is that I already have a positive charge. Right? So I don't want to get another positive charge on this oxygen. That would be an intermediate that's too high in energy, too unstable. So we avoid intermediates where there's two of the same formal charge. And under acidic conditions, we would also avoid negatively charged. Okay, so before we can protonate here, we need to deprotonate here. That will get us to neutral, and then we can get a positive charge. We also have the clue of looking to see, okay, we need to get to this acetal. We're very close, we just need to remove this group. Okay, so there's lots of ways you could think about it, okay, but the next step needs to be a proton transfer. So we will deprotonate. Get to a neutral species here, which also happens to be the hemiacetal intermediate. Okay, once we're neutral, now we need to think, okay, I do want to get rid of this, and I do need this to be a good leaving group. So we can protonate here now, and we'll not have an intermediate with more than one positive charge. So in order to protonate this oxygen, I need to draw in the acid. I can draw in my HA. We're going to pick up a proton. Remember, the goal of that is to make a good leaving group. Once that oxygen has been protonated, now it's a good. So now it can leave. And it's common also to show the lone pair forming a double bond to get to the most stable resonance. Though that's not necessary, it's okay to just draw this one arrow and have the positive charge here. The most stable resonance contributor puts the positive charge on the oxygen. That's why we've drawn that second. Forget all lone pairs and formal charges, and we did kick out some. Draw that as a byproduct. Remember, when this oxygen is positively charged, the carbon double bonded to it is super electric. Form the second carbon-oxygen bond to the acetal. This is the intermediate that's immediately formed from that nucleophilic attack. It's very close to the product. We just need to do a final proton transfer. Product, which is this guy, acetal. Okay, I did not label my steps, so I can go ahead and do that. But they'll be the same labels as we had before. Transfer, followed by a nucleophilic attack, followed by another proton transfer, and loss of a leaving group. A nucleophilic attack, right, so note how our intermediates were either neutral or had one positive charge. We very carefully avoided any steps that would ever have a negative formal charge or had an intermediate with two positive charges. So very unlikely. Okay. So now it talks about how the acetal formation is really reversible. So if we look at the ketone forming the acetal, it starts talking about the fact that you can back. So we would have to do something if we were doing this reaction in the forward direction. For example, using a large excess of methanol would drive the reaction forward. Right? And using a large amount of water would drive the reaction. So like a dilute solution. Good. Going back because we want a large amount of water to drive it back to the. So because the reaction is reversible and all the steps are reversible, when we go back, we're going to hit the exact same intermediates. If you compare these to the intermediates on the previous paper, what you'll notice is that the intermediates are the exact same, pretty much the exact same structure. So if it's reversible, we're going to go through the same path, just in reverse. We're going to draw the mechanism to go back from the acetal to the ketone. And We're going to follow all the same rules that we did before. Draw in all lone pairs. We're going to draw our curved arrows and label the steps. So we're going to start out with some pairs here. Right? And we have a strong acid. Right? From a neutral species like this, it's most likely going to be picking up proton transfer. We need to get this intermediate. Notice how this is a good leading. Protonated methoxy group is a good leading group. So we can pick it up, which is what we want to do anyway because we need it to go so that we can replace it with water. Get back to the loss of a leaving group. We draw 2 arrows that in order to get to the most stable resonance step. There. So we've kicked out a methanol. We're going to need to kick out another methanol, but we're getting it. So at this point, remember this carbon is highly electrophilic. So, and we have a lot of water around. Dilute acids. So lots of water, very electrophilic carbon, nucleophilic attraction. That gets us here, positively charged oxygen. So never protonate this as well. I know you want to get rid of it as a leading group, but you can't have an intermediate with positive charges. First thing to do is deprotonate this, then we can protonate. And I know it's tempting to draw it all in one step, like deprotonation and protonation all at once, but try to refrain yourself from doing that. Right? Just do one step at a time. Okay, so we're going to come in and protonate pairs. And now notice we've gotten to the heavy acid. Right? If we go there in the forward direction, we need to get there first. So I'll draw in some lone pairs. Remember, the goal now is to get rid of this group. We don't have a methyl there in the product. So in order to get rid of it, I can't kick it out right now because that would generate an oxygen with a negative charge. That's bad. Under acidic conditions, an oxygen with a negative charge is a strong base, and that's not likely to form under acidic conditions. So the best thing to do is create a good leaving group. So through proton transfer, we now have a good leaving group. And now that we have a good leaving group, if we and now we're really close to the product, we just need to do a final proton transfer. So this was basically going from the acetal back. The conditions that would favor that are, instead of having a bunch of methanol around, you would take this acetal and add dilute acid, lots of water around, which would drive the equilibrium. So whenever you have a reversible reaction, you should be thinking about blocking groups, protecting groups. You might be able to use that. So we are going to essentially use these same steps, right, to go back with the cyclic acetal. So it's going to be the exact same thing, right? That just looks a little bit different because instead of using an alcohol, right, we have to kick out a diol. But really, if you think about the root core of the steps. So the goal is to completely kick out this diol to get back to it. So this is neutral right now. Right? But there's strong acid around. So you can protonate it, make it more reactive. So we're going to do proton transfer. So now we have a good leaving group. Now that it's protonated, you can easily pick out the protonated oxygen. So loss of the leaving group. Next. Carefully drawing all lone pairs and formal charges. Remember, whenever you have this situation where the oxygen is positively charged, this carbon is highly electrophilic and can be attacked by a weak nucleophile. Remember, in the reverse reaction, there's lots of water around. So water will be the nucleophile. So we're at this intermediate here. We are close to the hemiacetal. We just need to lose. So yes, we want to get rid of this group up here, but we cannot protonate right now because we get two positive charges. The best thing to do is deprotonate this and reach the hemiacetal intermediate, and we'll get a neutral. So to do that, we are just going to use a generic conjugate base of the strong acid. Okay, so this is now the and we regenerated. Okay, from the hemiacetal, the goal is to get rid of this leaving group. We cannot do that right now. We have to protonate the oxygen first. So proton transfer, so nucleophilic attack, proton transfer. A proton transfer there. Now it's a good leaving group. Go ahead and do lots of leaving. At this point, we have now picked out the diol. So that's the other product form in reverse. Go ahead and draw that in. Leaving group. And we're very close to finishing up and getting the product. We just need to lone pairs do a proton transfer. So we can use this again for a final proton transfer. The product. And notice how we got the acid back in the last step. So we really only need a catalytic amount of acid. Okay, so practice drawing the mechanism to make an acetal in the forward direction and also in the reverse direction, noting that you're going to go through the same intermediates. now we're going to really do what amounts to a review reaction. We're treating a compound that has both a ketone and a cyclic ester with LAH. Right? So there will presumably be some sort of protein. Not mentioned there, but there would always be some sort of protein. So recall that a ketone will get reduced to a secondary alcohol, LAH, and an ester, right, gets reduced. We kick this out as a leaving group to get an aldehyde, which gets further reduced. We also have to assume that there's probably excess LAH, because in order to do a full reaction, we need at least 3 proteins. So to draw that out, we have the secondary alcohol here. And ends up, this carbon ends up being alcohol. We kicked, right, that other group out as well. End up actually with 3 alcohols. I call that a triol. Okay, so let's do some practice here. Let's pretend like we, well, I guess it doesn't. We'll talk about it after we do this. So the first thing we're doing is treating this compound with a diol and acid. So we're going to be forming an acetal. You might remember I told you that ketones are more electrophilic than esters. They will be selectively converted to. So the ketone will form an acetal and the ester will not. Ketones are more electrophilic, forming active. Alone. And then now we're treating with LAH. Okay, so we've this is no longer a ketone. So LAH is not going to be active, but it will still reduce the ester. So it does not react with acetal. Go ahead and reduce the ester, diol, and then now dilute acid, right, will remove acetal. Go back to ketone. We have devised a way to use an acetal as a protectant. Use it to protect ketone or an aldehyde from a reaction such as LAH, and then eventually deprotect and we prevented any reaction, in this case reduction of that carbonyl. By the way, acetals they're very labile, meaning they react under acidic conditions. They're very stable under basic conditions. LAH is like hydrides, it's a strong base. So for example, acetals would be a good protecting group as well if you want to utilize a Grignard reaction. Right? Having a ketone around during a Grignard reaction is not good unless you want to react that ketone. But if you don't want it, you might want to protect it. So once you protect it, it's going to be stable under your formula. We'll see how that's used later on in that. Okay, so now we're talking about the fact that normally we would continue to react after the hemiacetal. But in this particular case, because it's cyclic, it's much more stable than an acyclic hemiacetal. Right? So those often form and stay that way. So let's draw the mechanism for how we would form a cyclic hemiacetal. So whenever we're drawing a mechanism, of course, we're drawing lone pairs, and we're going to do a proton transfer with this strong acid protonate. And you might think, okay, where is it going to protonate? Is it going to protonate the oxygen of the alcohol? Is it going to protonate the oxygen of the ketone? It will do both. Right? It will do both. But they're reversible. So it might protonate the alcohol, but then go back. And that might happen several times, and eventually it might protonate. And when it protonates the ketone, then we can have a further reaction. So even though there's proton transfer going on with the alcohol, that doesn't help us get to the product. Don't draw that in. So we are going to do a proton transfer. Carbonyl. Remember that that generates a highly electrophilic carbonyl carbon. Right, so we can do a nucleophilic attack with the attached alcohol. The initial product here is this protonated oxygen, and we need to get to the neutral species in order to get to the acetal. So we would just use the conjugate base to do a final deprotonation. So in this case, we just did a proton transfer followed by a nucleophilic attack followed by a proton transfer. And it's stable at this cyclic hemiacetal and doesn't. By the way, this is a direct application to sugar chemistry. So sugars form these cyclic hemiacetals, and that's their primary form, is that stable cyclic, like glucose. Okay, so moving on to predicting the product of hemiacetal or acetal formations. Fill in the empty boxes with the proper structure. Okay, so we have cyclohexanone and the alcohol being used as so to draw the product, we need to draw, this will go all the way to an acetal. Draw the methyl acetal. Okay, so if you use a different alcohol like isopropanol, then you will get different R groups on those oxygens. Again, we're acetal. Okay, now we are using an aldehyde and ethanol. Really fine. Aldehydes also form acetals. Acetal from ethanol and that aldehyde. Here we have a ketone here, benzoic, and this alcohol, right? So that would be a neopentyl group. Alcohol. We can draw that in this small space. Or you could just use some sort of abbreviation. Okay. All right, now we're getting to, you're given the acetal, right? Figure out what was the organic starting material. So note that we have a hydrogen here. Because of that, we know that we started from an aldehyde. So to do that, it looks exactly like this. Starting material. And then we formed a cyclic acetal, so we utilized a diol. So we have the acid and the diol. There's 3 methylenes here, so it's OH, CH2, CH2, CH2. So that's how I know how many I have in my diol. From this one, notice again there's a hydrogen here, so it's an aldehyde. Again, so the starting material was benzaldehyde. Okay, and the R group is just a methyl group, so methanol. Okay, getting into the slightly more challenging ones. Right? Now we notice that the product is actually a hemiacetal, a cyclic hemiacetal. That's why it's stable. So this can be a little bit more challenging to see, right? But it's very likely that this was the attached alcohol that came in and attacked, that this oxygen came from the carbon. So to kind of distill that down to the reactant, and imagine the carbonyl here, right? And that forms this alcohol. And then attached here would be the alcohol that eventually does the attack. That can be a little bit more challenging to see. So in this case, we did not need any alcohol because the alcohol is attached. So how would you classify this one? This is a carbon with 2 OR groups. This is an acetal, just like the others. It might look a little different. You're like, oh, I don't recognize that. It doesn't look the same. But when you see a carbon with 2 OR groups, that's just an acetal. So that could be from a similar sort of reaction than we've been doing. So the way to potentially think about this is kind of like deconstruct it to something you might have been able to recognize before. So how do we make acetals, right? We make them with alcohols and a carbonyl. Okay, so if we kind of break those groups, those are going to be our alcohols, and then put carbonyl there. What kind of carbonyl? Well, notice that there's a hydrogen attached to that carbon. It's actually going to be, so if we think about it, what would that look like? Right? Put an aldehyde of that carbon, go off like this, and we have CH2, 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 and H. This one is the most challenging for sure to recognize. That if we think about where does an acetal come from, right? Because it comes from carbonyl and 2 alcohols. And these are just attached. Of course, we always need acidic conditions. Because the alcohols are attached, we don't need a second. Okay. So moving on, we're going to start working on synthesis. And really, I think the goal of the synthesis is that he's laid out in this activity, is to really focus on using an acetal as a protecting group. Right? You might think, okay, we can just make this through a series of electrophilic aromatic substitutions. That would actually be pretty challenging because these are both meta-directors. How do you get them to pair up to each other? That is an act. But another way you could make this bond is through a Grignard reaction. You could focus on potentially using a Grignard reaction. But whenever we use a Grignard reaction, remember, we can't have anything undesired in the reactant that might react. So we might need a protectant. So we're starting with benzene, right? And probably we can at least introduce one of these to an electrophilic aromatic substitution, so specifically a Friedel class acylation reaction. So at the very least, that would allow us to do one of these. But we can't do the second one. First of all, this is a meta-director, and it's moderately deactivated, so you wouldn't be able to do a Friedel class reaction. You can't actually introduce the second one, regardless. So now what we can do potentially is actually, this is a really terrible idea. Maybe I can introduce halogen first. Because the problem right now I have is that now that I've introduced this, anything else is going to go in the wrong position. I do not think this went out very well. So perhaps we can add a bromine first. That might be a better choice. Right? Because at least the bromine, which eventually we can do a Grignard reaction with, is an ortho-para director. That's critical, right? Because we need the next group to be introduced there. So now that we have a para director, now we can introduce. So now maybe we can introduce the other group through a Grignard reaction. The problem is that if I form a Grignard reagent here, it will attack another molecule's ketone. So I need to protect this. So we can, and typically people protect when using an acetal as a protecting group, they use a cyclic acetal, utilize a diol, as opposed to an alpha. This will protect this, which will make it stable through a Grignard reaction. So now that I have protected it, I can go ahead and form the Grignard reagent, magnesium, and introduce the 2 carbons that I want to add. And acidic workup, protonation, which is sometimes left off. By the way, the acidic workup, because it's an acid and acetals are acid sensitive, that may just go ahead and move your acetal back to without having to use a separate step to remove the acetal. So it's possible it gets removed in the acidic workup, or you draw the acetal and use dilute acid, so water and acid to remove this. And then from here, all we have to use is PCC oxidized alcohol. Sometimes you have to scrap whatever you change. You realize that isn't going. Okay, now we have the same sort of synthesis, except for we want these 2 groups meta one another. So if I was to now brominate first, that would be a problem because the bromine would be a para director. So it's actually in this case that I think I might want to do the ketone reaction first. Because as we mentioned before, which was a problem for our first synthesis, this is a meta director. So in this case, that's advantageous. I cannot add a second one. Because remember, I cannot do a Friedel-Crafts reaction on a moderately or strongly deactivated. So I won't be able to, unfortunately, add a second one for that same reaction. That would be convenient because it would only be 2 steps. The unfortunate part is that it doesn't work. However, I can add a chlorine or a bromine. So I can work with that. And again, because I have a meta director, it will go into the position that I want. We have the same sequence of steps now that we showed before. We're going to use a Grignard reaction to introduce the second carbon-carbon bond here. But we need to protect this first because it's not compatible. So go through the protection step, form the acetal. Now you can do your Grignard reaction. Magnesium, followed by aldehyde, followed by the acidic workup. Let's say, okay, maybe that acidic workup did not remove acetal. That's okay. You can just make sure to do an extended treatment with dilute acid for it to be removed. Oh, sorry. I'm supposed to not do that. Okay, so now we can just PCC. Okay, so we already need the carbon-carbon bond in the next one. So it looks like now we are going to be introducing one methyl ketone. And then meta to that, we have this 2-carbon bridge to an alcohol. The 2-carbon bridge to an alcohol like this, it makes me think of potentially making this bond Grignard with an epoxide. Whenever you have the 1, 2, and then you have the alcohol with the new carbon-carbon bond, that really screams out maybe you can use a Grignard with an epoxide. So the goal would be, right, get to this step here. We do the same 2 reactions to get to this intermediate like we did before. Then we could do a Grignard reaction with an epoxide. So you still need to protect the ketone, and it's just a different Grignard reaction. The first step is the Friedel-Crafts distillation reaction. Then, because this is a meta director, we'll be able to introduce bromine meta to the ketone. We would like to make this new carbon-carbon bond for a Grignard reaction, but first we need to protect the ketone. Otherwise, the Grignard could attack the ketone of a different molecule. So now that we have it protected, now it's a good time to do the Grignard reaction. Again, I'm going to use the epoxide instead. Okay, and at that point, that group installed nicely. If I need to do the protection of the acetal separately, do that with dilute acid. And we'll get to the product. Moving on to the next one. So we need to make this new carbon-carbon bond, right? So we've been utilizing Grignard reagents. We do the same thing here. But again, if we're going to utilize a Grignard reagent to make this new carbon-carbon bond, we need to protect it. So first, we'll probably go through an acetal protection. Right, and now we are able to do a Grignard reaction. I'm going to be adding 2 carbons here. Add 2 carbons. We initially get an alcohol here, so we're going to have to get rid of that. So we are going to oxidize with PCC, and one of the reactions you learned in this chapter is the Wolff-Kishner reduction. So we have the ketone, and the Wolff-Kishner is hydrazine. NH2, and acid, followed by potassium hydroxide and heat. And that will remove the ketone. can just do heat protection. Last one here. So now it looks like we need to make this new carbon-carbon bond. We introduce 3 more carbons and eventually get an epoxide. So we know that we can form epoxides with MCPDA through an alkene intermediate. Maybe the alkene came from an alkyne. But any sort of carbon-carbon bond forming reaction here, you should think about, do we need to protect the ketone? Depends on the type of carbon-carbon bond forming reaction you want to do. If you're going to utilize a Grignard, then you do. If you're going to utilize an alkanite ion, you don't. So in this case, we don't really, we can use it. But first, in order to do that, we need a leading group. So we need to brominate. So we can brominate in a benzoic, on a benzoic carbon. Now we have a good leading group, and we can introduce the carbons. Remember, we're adding 3 carbons to make sure we use the right alkyne. And in this case, we did not need to protect. This is not a strong enough basic conditions to be concerned about. So we were able to add those 3 carbons. We can notice the stereochemistry here, so the syn relationship. So we need to do the epoxidation from a cis alkene. So in order to get a cis alkene, we need hydrogen. Sure to generate that cis alkene so that we can get the correct stereochemistry for the last step. So there are definitely other possibilities for how to do these synthesis problems in some cases. So if you have an alternate pathway, go ahead and let me know. You can post it on the discussion board or email me and I'll happily. That concludes the activity today.